Hi, everyone, and welcome to Topological Data Analysis and Neuroscience. So in this week's videos, we're going to be talking about visualization and interpretation. Okay, so to start, we're going to focus on two different visualization methods in these videos. The first is multidimensional scaling. This is not exactly a pure topological method, but it is widely used in practice and a very powerful tool for visualization of metric spaces. The other tool we're going to look at is Mapper. This is a more topological data analysis specific technique, and it's a great tool for studying high dimensional data sets. And in particular, both of these methods here are great for dimensionality reduction, which is something that regular persistent homology doesn't accomplish. And then we're also going to look at methods for vectorizing barcodes. And these are important for machine learning workflows. In machine learning applications, you typically want vectors in Euclidean space for most existing algorithms. And unfortunately, persistence diagrams cannot be embedded isometrically in Euclidean space. So we'll look at a few ways of sort of forcing that embedding. Okay, so the first thing we're going to look at is multidimensional scaling. So the idea of multidimensional scaling is to take a finite metric space and find a way of embedding it into some Euclidean space. So for example, this picture right here, this picture consists of senators. So each point in this picture represents one senator in the US Senate. And there's a metric, you can define a metric on senators based on how frequently two senators vote together. So if two senators always vote, well, let's say they don't always vote exactly the same, otherwise their distance would be 0, right? Their voting patterns would be indistinguishable. So let's say two senators vote very closely, right? Maybe they only differ on a couple different votes, but for the most part, they usually vote the same. They're going to be very close together in this metric space. Meanwhile, if we have two senators that rarely vote together, we'd expect them to be very far apart in this metric. And so that's something interesting that we can do, is define this metric on senators. But the thing is, if we just define this metric, it's just going, how is that metric going to be given? Well, I mean, a metric is just a distance matrix, right? That's all there is to it, really. And so this is nice for computers. Computers can look at a distance matrix and see stuff in it. But for humans, large matrices are oftentimes very difficult to interpret, and it's tough to see what's going on. If I were to give you, like, even for the Senate example, which is a small example, this would still be a 100 by 100 matrix, and that can be very difficult to spot patterns in and see what's going on. So the idea with multidimensional scaling is that we want to take this finite metric space, which is not necessarily embedded anywhere, and we want to embed it into some low dimensional Euclidean space so that we can actually see what's going on. Yeah, and so what MDS will do is it's a method for taking any finite metric space and embedding it in Euclidean space. So like here, we have this voting pattern metric space, and we have it embedded into two-dimensional space. So now we can actually see what's going on here, right? We can see for if 2 points are close together, then we can assume that those corresponding senators vote very similarly. If 2 points are very far apart, we can assume they vote far apart, but we can actually see what's going on here. And we can see that there are certain clusters here. For example, we can see that there's really 2 main clusters with some sort of like some bridge in between. Those are representing moderates. For example, the far right blue dot represents a more conservative leaning Democrat, while the far left red dot represents a very liberal leaning Republican. And this data is anonymized, so we can't actually put names to the dots, but that's okay. We can still deduce information from this picture, right? From this picture, we can see that there are really two main clusters in the Senate, which matches with our intuition. And if I just gave you the distance matrix, that would be tough to see that in the matrix form. But with MDS, we can actually see it. Yeah, so MDS is very useful for human interpretation. But now there's a little bit of an issue with MDS, in that not every finite metric space can be embedded isometrically into Euclidean space. Right? This is what we want to do. We want to take our finite metric space and put it in Euclidean space in such a way that we're preserving all of the distances. But this is unfortunately not always possible. So for example, this metric space here on the right, this metric space is very simple. It only consists of 4 points, and the distances are labeled. So the distances between the sort of, I guess, adjacent pairs of points here are all 1, and then the distances between the diagonal pairs of points are all 2. This metric space here cannot be embedded in any Euclidean space. Right? You can't embed this isometrically into R2. You can't embed it into R3, R4, and so on and so on. Right? You just can't. It's impossible. So this is an issue, right? Because for MDS, we want to take our data set and embed it into Euclidean space, but this is saying we can't always do that. So what MDS will do is it will still give us an embedding. It's just that the embedding won't perfectly preserve distances. So it's not a perfect technique, but it'll still give us an embedding. And it'll still give us a way of visualizing this data. And one nice thing about MDS is that it can be used for dimensionality reduction. So if you take, for example, high dimensional data, you can tell your MDS algorithm that you want to use MDS to embed that data into, for example, 2-dimensional space. Or you could say you want to embed it in 3-dimensional space or 4-dimensional space. The higher dimension you pick, the better the MDS embedding will be. But the more complicated the embedding will be, right? Something embedded in 4-dimensional space is much more complicated than something embedded in 2-dimensional space. So there's a trade-off there. There's a balancing act, but it's nice that we have that choice, right? And with MDS, dimensionality reduction is very useful, and it's something that persistent homology does not accomplish. Persistent homology does give us this sort of topological simplification, which is very useful, but it doesn't reduce the dimensionality at all, right? If you have a 9-dimensional hole in your data set, the persistent homology will show you that there's a 9-dimensional hole in there. So MDS does accomplish dimensionality reduction, while persistence doesn't. Oh, yeah. And so for those of you familiar with the notion of principal component analysis in statistics, multidimensional scaling and principal component analysis are very closely related. And in fact, for a lot of cases, they are the same. Okay, so now the next tool we're going to look at is Mapper. So Mapper is it's a method in topological data analysis for both dimensionality reduction and visualizing data sets. So if we look here, what we have are basketball players, right? NBA players in here. And we can sort of put a metric on NBA players based on how similar their stats are. And then the idea is, okay, can we sort of reconstruct, right? Just knowing that metric, just knowing how similar players' stats are, can we reconstruct the sort of types of players we'd see in the NBA? And so this is what Mapper would look like, what Mapper looks like here. It's sort of clustering, but not just clustering. It's also telling us how the the clusters are related, which is, so it's a sort of refinement of clustering. So let's go over the algorithm here. So the input for Mapper is just going to be a finite metric space or a point cloud. The parameters, we need two parameters. One is a function. So this is usually called the lens function or a filter function. And the other parameter we need is a clustering algorithm to use. Okay, so now we can start the algorithm. So the first step of the algorithm is we're going to choose a cover of the range of this lens function here. So let's look at an example. So here, in this example, we have our data set is on the left. So our data set is just this point cloud of all the black dots. Right? This is a finite metric space, and all we have is just these black dots here and the distances between them. Now what we're going to do is we're going to start with this function f. This is the lens function. And in this example, f is just the projection, right? We're just basically projecting horizontally onto the real line. So in this case, right, f is just the height function, sort of. It takes each point to its height. We're just mapping horizontally. Okay, and so the first step is we're going to choose a cover for the range of this function. So that's what these U1, U2, U3, U4 are. They together cover the range of f. Okay, so now the next step. For each of these covering sets, what we're going to do is we're going to cluster the points in the inverse image of these covering sets, right? So for example, let's look at U1. So if we look at U1 right here, we're going to look at the inverse image of U1. So we're going to look at each point that maps via f into U1. So that's going to give us these 4 points on top of this shape here. And now what we're going to do is we're going to run a clustering algorithm on those 4 points. We can use sort of any clustering algorithm you want, but yeah, we're going to run a clustering algorithm here to get a cluster and, to get clusters. But in this case, with U1, there's only going to be one cluster here, right? These 4 points are all sort of together. Now, if we look at U2, with U2, if we look at the inverse image of U2, we see there's sort of, so the inverse image of U2 is going to be these 6 points between the green shaded lines here. So these sort of 6 points in the middle of the circle. And when we run the clustering algorithm on the inverse image of U2, we're going to get 2 clusters, right? Because we sort of have these 2 separate pieces. So we're going to get 2 clusters there. And then for the rest of the inverse images, we're just going to get 1 cluster. Okay, so we've done step 2, and now we're going to go on to step 3. So step 3, we're going to turn these clusters into a graph. So the vertices of this graph are going to be just the clusters. And we're going to put an edge between 2 clusters if the 2 clusters intersect at all. So this graph is what we have on the right here. So for example, the cluster, so let's look at the top of the graph again. So what we did there was we looked at the inverse image of U1, which gave us the 4 points on top of the graph. We clustered that and got just 1 cluster. So we have 1 point at the top of the graph. Now we look at the inverse image of U2. We get these 6 points divided into 2 clusters. But each of those clusters, right? So for example, the top point in the right cluster is also a point in the first cluster we started with. So we're going to put an edge between those 2. And so that's why we have this top right edge. But now also the top point in the left cluster for the second covering set is also the leftmost point in the cluster for the first covering set. And so that's why we get an edge between, right? That's why we get this top leftmost edge, and so on and so on. We just keep doing this, and this is how we get our mapper graph. Okay, so now let's talk about how mapper is used in practice. So we have some parameters here. So we have some choices to make. Let's look at common choices that people make. So a very common choice people use for the lens function is projection onto the first n principal components. And most often n will be 1 here, just to keep it simple and make the algorithm fast. But sometimes people use n equals 2. And you can really use n, right? N could be higher. It's just the larger n is, the less dimensionality reduction we're going to have. We want mapper to be accomplishing dimensionality reduction. So if we take n to be large, we're not going to get that. Of course, it'll capture more information, but it'll be harder to interpret. Okay, and so, yeah, but there's a whole bunch of choices you can use for lens functions. We're not going to go into those, but yeah, a common one is just projecting onto the first principal components. Clustering algorithms. So there's a whole bunch of clustering algorithms you can use. A sort of classic that's widely used in applications and industry is dbScan. I do want to note here that you don't want to use a hierarchical clustering algorithm like the single linkage clustering algorithms UL coded. You wouldn't want something like that because that doesn't give you discrete clusters. It gives you a hierarchy of clusters, and we want just discrete clusters here. So that's something that, like, for example, a clustering algorithm like dbScan accomplishes. And so, but there's sort of a trade-off with having parameters, right? So we have all of these parameters here. And so that gives us a lot of flexibility, right? There's a lot of room to fine-tune this algorithm. And so that's nice in a way, but it's also unfortunate in a way because of all these choices we have to make, we don't have the nice theoretical guarantees that regular persistent homology offers. Right? We don't have, in particular, stability and algebraic decomposition. So there's a trade-off with mapper. It has less theoretical guarantees, but more flexibility. Yeah, if you want to think of this in terms of machine learning, mapper is more of a supervised learning technique, while persistent homology is unsupervised. There's no parameters to choose or anything. It just works. Okay, so the next thing we're going to look at is methods for vectorizing persistence diagrams. Right, so with most machine learning methods, which is a pretty big area of research these days, there's tons and tons of algorithms and pipelines for machine learning. But the thing is, they usually start with Euclidean vectors, right? So they start with points embedded into Euclidean space, where, right, Euclidean space is just Rn with the 2 norm. Right, so the distance between 2 points is just the length of the line segment between those 2 points. And persistence diagrams can't be embedded into Euclidean space isometrically. So we don't have we don't have the structure here. So we're going to have to sort of figure something out if we want to use machine learning algorithms on persistence diagrams. So there's a couple techniques to accomplish this. We're going to look at 2 in this video. The first one is persistence landscapes, and the second one is persistence images. So persistence landscapes, we're going to start with a persistence module here. And remember persistent Betti numbers of the, right, if we have a persistence module, its persistent Betti numbers are just given by taking the rank of the maps between right? Remember our persistence module, we have vector spaces. We have a vector space for each t in the real line. And then we also have maps, right? So if t is less than or equal to t prime, we're gonna have a linear map from vt to vt prime. The persistent Betti numbers are just take the rank of those maps, right? So if I have a point I and j with I less than or equal to j, the persistent Betti number beta ij is just going to be, well, we have a map from vi to vj. What's the rank of that map? That's what the persistent Betti numbers are. Okay, so the persistence landscape of this persistence module is going to be a sequence of functions. And these are going to be functions defined on the real line and mapping into the interval from minus infinity to infinity. And so that's just the extended real line, right? The real line, but we're including infinity and minus infinity. And they're going to be defined as with this formula here. So lambda k of t is the supremum. If you don't know what the supremum is, just think the max here. This is going to be essentially the max over all. It's the largest value m such that such that if we look at right, it's the largest value m such that if we look at the interval of radius m around t, that interval will have that the rank of that, or right. So okay, so let's fix our t, right? We have a vector space at t, but now if we sort of thicken that, so we take an interval of radius m around t, we're gonna have a vector space on the left and a vector space on the right. And we're gonna have a map from the vector space on the left to the vector space on the right. Now what this lambda k of t is doing is we want to take sort of the largest interval possible such that the rank of that map from the left endpoint to the right endpoint is at least k. And so that's what this function lambda k is doing. So if we look at an example here, so in the top left of this picture is just the barcode. The blue points are the barcode or persistence diagram here. I guess it's drawn more as a persistence diagram in this picture. But then what the numbers represent in the lines are the persistent Betti numbers. And then, okay, now we're going from the top left picture to the top right picture. And all we're doing is we're just taking this picture and we're rotating it 45 degrees. And pictured below it is the barcode that's equivalent to the persistence diagram. And now in the bottom left corner, we see the persistence landscape. So the function lambda1 is this function we saw on the last page, same with lambda2 and lambda3. And in this picture, there's no lambda4 or 5 or 6. They're all 0. Well, they exist. They're just 0 here. Okay, so let's look at how we can interpret these. Right, so these persistence landscape functions, they offer insight into, right, what they do is they tell us how long the kth most dominant feature surrounding a step t in our filtration survives around t. Right, so if we look at lambda1 of t is going to tell us, right, how long on either side of t did the feature that survives the longest around t survive for. Lambda2 is going to tell us how long the homological feature that survives for the second longest on either side of t survives for. Lambda3 is going to tell us about the third longest feature around t, and so on and so on. And persistence landscapes have really nice statistical properties. So in particular, they obey the central limit theorem and a strong law of large numbers. So they're very nice statistically. They have a lot of nice properties, and they can be embedded in Euclidean space. So you can use machine learning algorithms sort of in a just plug and play fashion with persistence landscapes. So it's very nice. And oh, and I should mention they are also satisfy stability as well. Okay, the next thing we're going to look at is persistence images. So persistence images are another method for converting persistence diagrams into Euclidean vectors. And so the way this method works is the idea is, okay, so we start with our data set, we take a persistence diagram, and now once we have this persistence diagram, so if we look at this picture of the pipeline down at the bottom, our data set is this thing on the left. And we take the persistence diagram and we move over to this thing just to the right of it. The next thing they're doing is something that was also done in the persistence landscape case, which was just rotate the persistence diagram 45 degrees. That's all this picture T of B is. It's just take the diagram and rotate it 45 degrees, just so it's not supported above the diagonal, but just in the upper half plane. And then what they're doing is they're placing Gaussians, like a Gaussian normal distribution over each point in the diagram and adding them all up. And what you do there is you get a function. And they do a little tricks with the function, but the idea then is that you can then place a grid over the plane and integrate with respect to this grid. And once you do that, you'll get that's what we're seeing on the far right of this picture, is this sort of heat map thing. But it's discrete, which means it can be represented in finite dimensional Euclidean space, which is very nice for, right, we're gonna have Euclidean vectors again, so we can work with those. Right, and so persistence images are also stable, just like persistence landscapes, and they can be used with existing machine learning algorithms as well. So these are two different techniques for vectorizing persistent homology. Both are widely used and are pretty successful. Okay, so now let's look at how we can put this all together. So we're going to look at sort of a common persistent homology workflow here. So we're going to start, so in persistent homology, the way the workflow usually goes is we're going to start with our data, right? So our data is going to be a finite metric space, or we might have multiple finite metric spaces. And then what we're going to do is we're going to take those finite metric spaces and turn them into filtrations for persistent homology. That's what we'll do. Right? So oftentimes the ones used are RIPS filtrations, although there are other choices as well. Now we're going to take these filtrations and turn them into barcodes or persistence diagrams equivalently. And now you can stop here, right? And this is what some people do, is stop here at the barcode level and interpret them, have a human interpret them and try to figure out what's going on. But also from here, we can keep going and we can take our persistence diagrams and vectorize them and then use those vectors for machine learning algorithms. Or something else we can do is we can take those persistence diagrams, compute bottleneck distances between each of the persistence diagrams. And then we can either use clustering algorithms or MDF or multidimensional scaling to visualize what's going on there as a sort of topological simplification step, right? Just getting the essential structure. And so these are sort of the ways that persistent homology is typically used in practice. And yeah, so that's it for this week's videos, and thanks for watching.